what I'd like to just talk to you guys about is kind of the overarching picture of where things are going these days in my lab. So as you know, I'm interested in brain-body interactions, and I'm particularly interested in how the hierarchical and distributed structure of neural control of, in particular, tendon-driven systems allows us to understand how is it that organisms function. Because in a sense, what's fantastic about how animals and others and humans operate in the world is not that they work so well, but actually that they work at all. When you put together the demands of the physics together with the properties of neurons and tissue and delays and noise and uncertainty and stochasticity, it's incredible that we all even work. And in fact, we could even argue that, and I did argue in my book, that we're actually operating at the edge of failure. Even though we seem to be robust, I think this crowd understands better than most that these are usually adaptations to disability, that we can postpone overt dysfunction by adapting in a variety of ways until you can't adapt anymore, and then the disability becomes overt. So I'd like to remind people that BME 504 is offered in the fall of 2021. I do hope that you will send your students. It'll be in person, as Jim says, but also with Zoom add-ons and stuff. And so the basic idea is that you have the neural dynamics of the central controller, the brain, and then you have the lower level spinal and muscle dynamics. And then you have the physics of the body that's interacting with the physics of the world. So what we're doing is we're studying this in humans and what we call neurorobots. So they're robots that are implementing the fundamental principles, at least as we understand them, of neuromuscular control. And we're applying this in particular, say, with Carol Lee and with Chris and Yonggang and Sukli Liu and Jason. We want to understand how is it that stroke rehab can be seen from this perspective, looking at brainstem function, which is not cortical, but rather it's further down the control strategy, how that interacts with spinal and muscle dynamics to tell us how function is compromised in stroke and paths for rehabilitation. But at the same time, we are building physical robots that have what are called neuromorphic circuits. These are computer chips that are emulating spike populations of spiking neurons that then feed motors and amplifiers and the like that actually produce manipulation and locomotion. And so that's what I want to share with you. I'm in a place where we are actually thinking of animals and robots as equally valid and informative ways to test hypotheses of how neuromechanics happens in this physical world.